I want to show you all the basic gates available in Logisim, and you can find them in here in the gates section. And of course, we have the OR, the AND, and the NOT gates, which we always know, but we have also other gates. For example, we have a NOR gate. You see the symbol, the electrical symbol of the NOR gate, which is identical to a OR with a circle in the output. This little circle in the output means that a NOR gate behaves like a negated OR gate. So the truth table is basically the opposite of the truth table of the OR gate. You see, we have 1 only when both the input are equal to 0. And in a similar way, we have an AND gate, which basically is the opposite of a AND gate. You see, even here we have a circle in the output. So the truth table is the opposite of the truth table of the OR gate. And we have, in addition to these, we have other 2 gates. By the way, you can move around the circuit using the AND tool. And here, down here, we have an XOR gate, or exclusive OR gate, which we already met in a previous video, this one. And basically, the XOR gate gives 1 whenever the 2 inputs are different. So if we have 0 and 0 or 1 and 1, the output is 1. And when the 2 inputs are different, for example, 0, 1 or 1, 0, we have 1 in output. And finally, we have an XNOR gate, which is an XOR gate with a negation, with a not in the output. So the truth table of the XNOR, exclusive NOR gate, is the same of the exclusive OR, but the opposite. It's the opposite because in this case, we have 1 whenever the 2 inputs are equal, 0, 0 or 1, 1, and 0 in the other case. So the first question of all is, all these gates are really necessary? And of course, the answer is no. We have already seen, as told before, another way to realize an XOR gate, but it is easy to show that we can, for example, have a OR gate and simply put a NOT in the output, and this is a different way to realize an OR gate, a NOR gate. So basically, all these gates are, it is possible to build them using the basic AND, OR, and NOT gate. And by the way, there are literally infinite ways to realize a given truth table. I'll give you a quick demonstration. So, for example, this is a OR, but if I put 2 NOT in the outputs, I have also a OR. This is also a OR because the 2 NOT in cascade, in this type of connection, erase each other, so it's one, it's the opposite of the other one. So this is another way to realize a OR gate. And if I put the other 2 not in the output, I have still another way to implement a OR gate. I can go literally to the infinite. So this is a sort of demonstration that it is possible to find infinite circuits that realize a single truth table. This doesn't mean, of course, that all these circuits are equivalent in cost, effectiveness, dimensions, performance, and so on. In general, a circuit designer's task is to find given a certain truth table, to find the best circuit that realizes it. Of course, this is not the best way to realize a OR gate. And usually the best way is the circuit with the least number of logical gates, but that's not always the case. We'll see it in the future. Another question is, do these standard gates exhaust all the possible truth tables, or at least all the possible truth tables with just two inputs? And here the answer is no. I can quickly show you a circuit that doesn't fit in any of this one. So let's see which is the truth table of this circuit. So 0, 0 gives 0, 0, 1 gives 1 in output, 1, 0 gives 0, and 1, 1 gives 0, 2. So you can see that there is just one case in which the output is 1, and this particular circuit is different from all the basic gates. There is no other simple gates with this truth table, this behavior. So it is possible to have some circuit with a behavior different from these basic gates. And one last question. Given a truth table, will be always possible to realize it using standard logic gates? In other words, is any logic circuit feasible, or there are some maybe very complicated truth tables which are impossible to build, to realize? Well, the answer is no. Any truth table can be realized using only and, or, and not. This is a consequence of a very important theorem, a very important theorem of Boolean algebra, which is the branch of mathematics that deals with binary logic. This is the Boole's expansion theorem. In a nutshell, this theorem ensures that given a truth table, even a very complicated one, will be always possible to find a circuit that realizes it. Using just the three basic gates, so fundamentally, we can realize every circuit, every logical circuit, using just or, and not. Look at this circuit. You see that using a single NAND, I can realize a not. This is a quite strange circuit because I have connected the two inputs of the AND, and in this way I have just one input, and this circuit has the same truth table as a NOT. And using two NAND gates connected in this way, I can implement an AND. Of course, because this is an NAND with a NOT in the output, the result is an AND gate. And finally, using three NAND gates, I can have a OR equivalent. So you see, in this case, with this circuit, the truth table is equal to the truth table of the OR. And in quite similar way, using only NOR gates, we can implement the NOT, the OR, and also the AND. So basically, all the three basic gate, not and or, are feasible using only NAND or only NOR. So in a way, you can build any logic circuit using just one logic gate. You can use just NAND or just NOR, and you can uh, build any circuit, any truth table you can think about.